Problem 10.6. Medical facility does MRIs for sports injuries. Occasionally, a test yields inconclusive results and must be repeated. So this is the process, okay? The process of performing MRIs for sports injuries. Using the following sample data and N of 200, determine the upper and lower control limits for the fraction of retests using 2 sigma limits. So what is the, in this problem, how would you define X? The variable of interest or the item of interest. John? Well, yeah, eventually it will be proportion, but we will define X as the number of inconclusive readings in each sample. Right? And what is the sample size? What's the N? 200. So eventually we will be computing a proportion because we can convert X in relation to the sample size. So the appropriate chart here will be the P chart or the proportion chart. And the formula for the proportion chart will be this. Okay. I'm going to copy the data from the Word file. I don't have to retype them. Okay, so there you go. Make it too small. All right, so that's the data. The number of inconclusive results is how we define as defectives. So for each of these samples, we're going to compute a sample proportion, which is equal to X divided by N. All right? So we will convert 1 as a proportion divided by 200. Okay, I need to change the format so that I'll have it's 0.005. And I'll just copy this across. These are our sample proportions, which we will need to plot on a control chart, a P chart. So using this formula as our guide, we will compute the upper control limit as well as the lower control limit. So for this formula, we will need P bar. P bar is nothing more than the average of the sample proportions. All right, so this is, we'll call this P bar, or the average proportion. And that's it. That's all we need. Oh, the Z value here, the Z score? Well, the problem says compute a 2 sigma. When it says 2 sigma limit, this actually means Z is equal to 2, or 2 standard deviations above and below the mean. So for a 2 sigma limit, what confidence level does this translate into? Is it 98 or 95? Yeah, somewhere between. It's 1.96, yeah, so it's around about 95%. Okay, now we convert this formula into the Excel formula. It says P bar. P bar is this. Okay, make that into an absolute address. Plus the sigma. Let me do this. Let me go back and say this is Z. And I'll put here 2. And again, the idea is that we can change this, the sigma, and the control chart will change with it as well. All right. Equals this. Press the F4 key. Plus sigma, which is that. All right. Press the F4 key. Times, it says the square root of the entire P bar times 1 minus P bar divided by N. So Excel's function is SQRT for square root. The square root of, and be careful with using your parentheses here, because what we want to do is to multiply P bar, which is this, again F4, times, open parenthesis 1 minus P bar, F4. Okay, so you see that this part here is really the numerator of this formula. And then divide this whole thing by 200, the sample size. Okay, you guys okay with this so far? Instead of 200, putting 200 here, I'm going to put in and 200. That's the sample size. So I'll just replace 200 with the address of the sample size, make that in 2. The formula for computing the lower control limit is basically the same as the upper control limit, with the exception of we will subtract instead of add the margin of error. So I just copied this formula down here and change the plus sign to a negative sign. Now, when we're talking about proportions, what is the lowest value we can possibly have? 0. But in this case, it's saying negative. So the temptation is to just replace this with 0. Don't. What is a better approach? Use an if statement, correct. So we will do this. Equals, so the if statement is if the computed lower control limit is less than 0, we will ask Excel to put 0, else compute the lower control limit. Okay, so that's kind of the syntax that we are going to use to compute the lower control limit. So we'll translate this statement onto here. It will look, once we're done with this formula, it'll look really scary, but don't be scared, because what we've done up here is we have computed the LCL, or the lower control limit. So what you can do is copy this, copy that formula, and then just edit this to include the if statement. If LCL, remember I copied the LCL formula, so I'm just going to paste it back there, is less than 0, comma, 0, else compute the lower control limit. So look, if you're reviewing this, it looks scary, doesn't it? But build it one formula at a time. Then it becomes much easier to deal with. There you go. 0. We'll just copy this across. Hopefully my formulas are correct. Yes, they are. So we'll add one more line, which is the center line. The center line is the P bar. F4. Copy that across. And we have the 3 rows to have our control chart. The upper, the center, and the lower limits. Insert. Line. Are we clear so far? So what do we plot? What do we plot onto that graph that just disappeared? Things are not working out well today for some reason.
You said good morning.
I don't think I said good morning to you today. Okay, so we need to next plot the sample proportions onto this graph. Select data, add, and we'll call this proportion, sample proportion. The series values are this row, and then click OK. One more time. There it is. There it is. What's our conclusion? Yeah. 0. It's just not showing it, but that's the, it's green. It's not showing. So based on this graph, what can we say about the MRI process? During this period, it was out of control. Specifically, what period? So that's the 10th observation, is that it? Okay, which is this. So we want to investigate what happened on this 10th observation. Could be the machine needed some calibration, or a person operating the MRI, a new person. Okay, look for the reason why there were more inconclusive results on this period than what you might accept. So Vanessa earlier asked the question, what should we do in case we observe something like this? Well, the problem asks you to determine if the process is in control, and then, if not, eliminate any values that are outside the limits and compute the revised limits. To recompute the revised limits will require a simple delete operation. There you go. Now you've established a better control or standards for future MRI readings. Okay, questions? Vanessa? Well, if they were all below the center line, that means that you may have improved the process, that the proportion would have shifted downwards. So you need to create right. Anytime you introduce, you change a process, introduce a new system, you would want to recreate a chart to see if it indeed improved, what you're trying to monitor. In this case, number of inconclusive results.
So 10th sample?
No, you're not, because the 10th sample is not representative of your typical process. Maybe on that date you had a machine that need so okay. Now here's a question, perhaps that you obviously the objective is to get as few inconclusive results as possible. In fact, maybe 0. Suppose that at some time you didn't make any change to the process, but you observed, 0 inconclusive results in, say, 3 or 4 successive points. Would that be good or would that be bad? That's right. You still have to investigate, why, you had that good results during that period. Is it really because of, something, everything went well during those periods? Or it could be that, the person reading the MRI is passing everything. Meaning maybe it's inconclusive result, but the person, what do you call that person? The radiologist or whoever reads the MRI doesn't know what he or she is doing, that everything is good. When in fact some MRI readings are not. The technician. Okay, so are we clear here? And then next problem then. Problem number 10-7. The postmaster of a western city, small western city, receives a certain number of complaints each day about mail delivery. Assume that the distribution of daily complaints is Poisson. We talked about this distribution before. Poisson is when you want to observe number of occurrences in an interval. In this case, the interval is day. Construct a control chart with 3 sigma limits using the following data. So once again, we will define X. What is X in this case? Number of complaints per day. So we're dealing with an attribute. Question for you is, can we convert X in this case in terms of a proportion? No, we cannot, because we're really, the maximum number for X is infinite. So the appropriate chart here is known as the C chart. C chart is used when you simply want to observe number of occurrences in a given interval. The formula for the C chart is given here. Here it is. Okay, and we will need to copy the data. All right, make this a little bit narrower. So just as before, we will need to compute the upper control limit, the lower control limit, and then center line. Center line is the average of these observations. We also call that C bar. C bar. Next, we convert this formula into Excel formula equals C bar, which is this, F4 plus the sigma limits that they want us to construct is 3. So which translates into what confidence level? 99.7. 3 times the square root of C bar, which is Q5, absolute cell. You follow so far? Oh, sorry, this is not, this should be plus, not multiplication. That's why it's too high. Can't be that high. There you go. That's more like it. Copy this down. Change the plus to minus. And once again, we're talking about number of occurrences per time interval, so the minimum value should be 0. So we can edit this formula to include the if statement. If the LCL is less than 0, ask Excel to return 0, else compute the lower control limit. Copy this across. That should be right. Good. The center line is simply Q5. Copy that across. Brother, you don't want to be copying that formula. You probably just want to make sure that you do it this way.
Right.
Okay?
That's right. Yeah.
All right. Then we insert line, and there's our basic chart on where we will plot these numbers. Right-click, select data. I'm going to add another series, and I'll call this number of complaints. The series values are found from C5 to P5. There you go. 1, 2, 3, 4. So would you consider this 1, 2, 3, 4 as a pattern? That's only 0.5 to the 4th power is What percent is that? Yeah, 0.6 is 6%. Given a z-score of 3, we are going to say that this is at least at this point is, well, we'll consider that as random. Okay, so I think this is a good stopping point. You know, the next one is, I have that on digitized lectures. Yes, Bo? Problem 18. This is something that I've had an experience with, doing a consulting job in Chicago, 95, in a printing press. You know, in a printing, we're not talking about a simple, you know, Kinko's type printing business, but rather a company, R Donnelley and Sons, and they print books, you know, telephone books, and you know how thick they are and how expensive it is to print these kinds of products. And in the printing process, you have a series of phases where in each phase, let's simplify it. First, the pages are printed, and then once the pages are printed, they're collated. And then once they're collated, they're trimmed, and then they're bound and then shipped to client or customer. Okay? A customer order, say, 1,000 units. If you were the printing foreperson, how many units will you start with? Knowing that this process is not perfect, meaning on this stage there will be some defective units and some will be usable, and these useful units will go to the next stage. Some of these will be scraps or defective, some will be useful. Only this useful part will go to the next stage. In the end, the customer needs 1,000 units, you better meet these 1,000 units. What happens if you run short? You're only able to produce 997. There might be a penalty to pay. Or you have to do another run. And in this kind of business, doing another run involves high setup cost. Prepping the printing machine, prepping the collating machine, and the trimming machine. Okay, so essentially you would want to have just one setup, and that you're able to meet the required or the ordered number of units. What happens if you say very conservative? You started with 2,000 units to account for the death rates along the way, that in the end you produce 1,500 usable units. That's right. Customer only pays for 1,000 units. What happens to the 500? That's cost to you. You can't inventory books, telephone books. You can't sell it, right? So the idea is to know how many you start with so that you're close to, or at least meeting, the required number of units. And how do you determine the starting point, the starting amount? By understanding your process. You know, what is the success rate on this stage? What is the success rate on this stage? Success rate on this stage. The same concept applies in like the fisheries industry. Anybody here who works for the Fish and Wildlife Agency? You know, they stock fish in a certain lake. You know, how many small fish do they start with? Well, you determine on what is the number of fish that need to be harvested. You go back. What's the death rate from roe to what's the next stage? Fingerlings, whatever. The different stages, there are death rates. Understanding the death rates is important in determining or meeting the target. So for this particular problem, the defect rates are stated. Are they not? First stage, what's the defect rate? What? 10%. Okay. Next stage, 6%. Next stage, 6%. This is the defect rate. Or you can call this mortality rate, death rate, whatever rate you want to call it. If we subtracted this 0.1 from 1, you get the harvest rate, or the success rate, which is equal to 0.9, 0.94, and 0.94. The target number of units in the problem is 450. They want to be able to produce 450 good units, given that the death rates are 10%, 6%, and 6% for the first three stages and for the three stages. How many should you start with? You know that you will not start with 450. You will start with something higher than 450 to allow for these scrap rates. What's the answer? Mandy? 549? Okay. 549, Mandy's... okay, we'll check it. Anybody else? Brendan? 560? 66? Okay, now we have two numbers. 570. Gentleman back there. Going, gone, sold to... Which one is the right answer? Okay, how did you... so Kristen is also getting 566? You know that's the answer. Well, how did you get 566, Brendan? Okay, so you multiplied 0.90 times 0.94 times 0.94. Okay. Okay, so this is Brendan's approach. Andy, how did you approach the problem? Oh, so you started here. Okay. Now, so you multiply this 0.1 with 450? What are you doing? When you multiply 450... Which of, let me ask the class. Which is the right approach? This approach or the approach that uses the defect rate multiplied by 450? Remember, you cannot, because it gives you two different answers. Only one of the answers above is correct. 542. Now let's look at this intuitively. Okay? Intuitively. We know that this is the unknown, x, the starting point. Okay? of this starting point on the first phase, only 90% will survive. Okay? So if you say x times 0.9, this becomes, the sex stress, the number of successes after the first stage, which goes into the second. And then of these, x times 0.9, which is the usable units after the first phase, how many will survive? 94%, 0.94. And that becomes the usable units on the third phase. X times 0.9 times 0.94, that was the number of unit successful units through the second stage, and of that 94% will survive. This is equal to 450. So this is the correct formulation. Okay? 450 divided by the 0.9 times 0.94 times 0.94 is your x. What is the consequence when you have a process, a phase, that is very unreliable? Let's say that printing is unreliable, that your success rate is actually less than 90%. You start more, right? Your cost is higher. So how do you address reduction in costs? By improving the process, making the success rate higher. You can do that through buying new machines, maintaining the machines more often. Okay? I think that's it. Questions? See you on Wednesday. Michael, you get the day off tomorrow. You're welcome. What, Clark?